so example E looks at solving another logarithmic equation. And what you'll notice is that in this logarithmic equation, there are more than one logarithmic term that has a variable in it. So what I'll do first is rearrange it. Ideally, when you're solving a logarithmic equation, you want to have all the numerical terms on one side, so like having 1 on one side, and then having all the logarithmic terms that have a variable in it on the other side. So what I'll do first is move the negative log x minus 4 to the right hand side. So I'm going to add it to both sides. So I get 1 equals log of x plus 5 plus log of x minus 4. And now using the product law of logarithms, because I'm adding two logarithms, I know that I can multiply the expression that's part of the logarithm. And so I get 1 equals the log of x plus 5 multiplied with x minus 4. Okay, so using the product law of logarithms, I can combine those two logarithmic parts. And so what you'll notice now is that I have one big expression on the right hand side and one expression on the left hand side. And so I can actually rewrite this as an exponential equation. And I know that this is a common logarithm with a base of 10. So I can actually rewrite this as 10 to the exponent 1 equals the product that I have here. Okay, so that'll eliminate the logarithm. So I get 10 to the exponent 1 equals x plus 5 times x minus 4. Okay, now the benefit to using, the reason, not really the benefit, but the reason why I use an exponential equation in this case is because I don't have a logarithm on the left hand side so that I could just equate both sides of the equation. So I had to actually rewrite this as an exponential function. Whereas the previous example we looked at looked similar with the two logarithms with the variables in them, except in this one you had a logarithm on both sides, so you could just set the expressions equal to each other. In this case, I only have a logarithmic expression on one side, so I can't just set both sides equal to each other. Instead, I have to write it as an exponential function, okay, or exponential equation. So now I'm going to expand the right hand side, and I get 10 equals x squared plus x minus 20. So x times x is x squared, minus 4x plus 5x is just 1x, and then minus 20. Now if I get everything to one side and I try to solve from there, I know I have a quadratic equation. So this would be 0 equals x squared plus x minus 30. And then this is actually factorable, so I'm going to factor it to get x plus 6 and x minus 5. So product is negative 30 and the sum is positive 1. And so what that means is either x equals negative 6 or x equals 5. And again, because I have two solutions, I need to check to make sure that both of them are valid, or if any of them are valid for that matter. So let's take a look at the first one. If I plug in negative 6 into our original logarithmic equation, negative 6 minus 4 will give me negative 10, which becomes extraneous because the logarithm of a negative number cannot exist. The expression has to always be positive. Logarithms only exist for values that are positive. So I know automatically that this solution here is extraneous. And so x equals 5. Let's check to make sure this one works. If I plug in 5 here, 5 minus 4 is 1, so that works. 5 plus 5 is 10, so that works as well. So this is the only solution that we have that is valid, x equal to positive 5. Okay, let's take a look at the next one. We have log of x plus 2 plus the log of 2x minus 1 equals 1. And again, similar idea. You have all the logarithmic expressions that have a variable in it on one side. So I can apply the product law of logarithms to get log of x plus 2 times 2x minus 1 equals 1. And again, because I only have a logarithm on one side, I can use the, I can rewrite this as an exponential equation. So the base here is 10. So I can rewrite this as 10 to the exponent 1 equals x plus 2 times 2x minus 1. And so I get 10 equals, if I expand and simplify, 2x squared minus x plus 4x is plus 3x, and then minus 2. And again, rearrange this. to get 0 equals 2x squared plus 3x minus 12. Now let's take a look to see whether or not this is something factorable. So the product would be negative 24, the sum would be 3, and if we think about this, I don't think there's a pair of numbers that will satisfy this equation. So if it's not factorable, your other option is to solve using the quadratic formula. So let's do that. X equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. And so I get x equals negative 3 plus or minus the square root of, we'll do this on the calculator quickly, so 9 minus 4 times 2 times 12, and you get the square root of 105 over 4. And so that means x equals negative 3 plus the square root of 105 over 4, or x equals negative 3 minus the square root of 105 divided by 4. Okay, so if we find an approximate answer for x, sorry, the paper is moving all over the place. So for the first one, you have x is approximately equal to square root of 105 plus negative 3 divided by 4. You get 1.81 approximately. And if I do the same thing for the next one, I get x is approximately equal to negative 3.31. Now if we try to see which solution makes sense, let's plug it back into the original expression, or the original equation that we had. If I plug in positive 1.81, I get positive plus positive, which is a positive result. So that value so far is good. If I plug it into the next one, 2 times 1.81 is a value that's greater than 1. So I know that this solution so far makes sense. So there's the exact value and the approximate value for x. So that one's fine. Okay, if we look at the next one, if I plug in negative 3.31, negative 3.31 plus 2 automatically gives me a value that's less than 0. So this value here ends up being extraneous. Okay, so again, we only have one solution that's valid. In this case, we did have to use the quadratic formula because our solution was a little bit messy. But regardless, you're just solving it like you normally would. Use the techniques that you know from before.